because I took everything out of it and left that way by itself.
Oh, well, that's a good idea.
Would rather the fact that
Good afternoon, everyone. I'm Megan with the Innovation District. I know we're a few minutes early. Obviously we'll wait till 1 o'clock and allow more people to hop on. But just a little bit of housekeeping as you sign on, if you wouldn't mind going ahead and muting yourselves, and then we can unmute once we get to the Q&A. So we'll get started here in about 7 or 8 minutes. Hey Liz, how are you?
Hi.
For those who just joined a couple minutes ago, I'll give folks another 5 or so minutes to sign on, but it looks like most everyone is muted, but we'll try to keep everyone muted or ask that everyone stay muted until we get to Q&A, just to cut down on that background noise. And we'll get started here in just a few minutes. All right, well, it is 1 o'clock. We have a lot of great content to cover, so I want to go ahead and get started. I know that we had a full roster of people who signed up, so I'm sure that there will be more people hopping on here in just a few minutes. But just a quick, well, first of all, I'm Megan Allen, Director of Projects and Programs for Oklahoma City's Innovation District. So glad that you guys all are joining us today. Couple of quick housekeeping items for the call. Looks like most everyone is muted. If you could stay that way until we get to the Q&A, that would really help to cut down on background noise. This presentation is also being recorded. We look forward to hosting this on our website and some other platforms. That way people have the opportunity to go back and listen as they are able. The other thing, we are trying to keep this at an hour. But it will likely run over as these things are wont to do. So if you need to hop off right at 2, that is no problem. No problem at all. So jumping right into it, the Oklahoma City Innovation District, our role really is to help any organizations, any people, any schools, any institutions really working in the area of innovation connect with one another through networking and programming. To really sort of drive forward an innovation economy and system. And so one of our programming initiatives was to host an annual symposium on a variety of topics that really cross-cut multiple industries. And we were looking forward to hosting an annual symposium on autonomous systems this past April. But as everyone can imagine, we had to cancel due to the pandemic. So we have been working to try to take some of the presentations we would have held in April to a virtual format. And Liz Pillar and the OU School of Meteorology were just phenomenal to work with. They jumped right at the chance to do this.
I am not giving up on this stuff.
Okay.
I'm riding her as hard as I can.
Just a reminder, if everyone can mute, that would be wonderful. Thank you. Anyway, so Liz and her team at OU School of Meteorology were instrumental in helping us launch this series, and we're really excited to highlight them today. So before I jump in, I also wanted to remind everyone this right now is a 2-part series. So today is the first of the series. We'll be doing the next one on June 25th. And so if you haven't already signed up for that one, be sure to do that. We are keeping registration for this purposefully minimized at 20 to 25 people because we really want to allow for that interactive Q&A. So with that being said, it's my pleasure to introduce Elizabeth Pillar-Little. She's going to tell you a little bit more about the Center for Autonomous Sensing and Sampling at OU and introduce the 2 students who will be presenting today, Tony Segalis and Tyler Bell. And just so Tony and Tyler are aware, we have the settings set so that you are able to share your screen whenever you are ready. So Liz is the Assistant Director for the Center for Autonomous Sensing and Sampling at OU, where she is responsible for coordinating the field deployments of UAS teams from both an operational and scientific perspective. She also ensures the continuity of day-to-day sensor business and enjoys spearheading outreach and science communication activities on behalf of the center. She is also appointed as a research scientist in the School of Meteorology and leads the atmospheric chemistry research of CAST. Her research interests are broadly centered around atmospheric and environmental chemistry, but she is very passionate about atmospheric composition, aerosol optical properties and composition, and the interplay between aerosols and convection initiation. Dr. Pillar-Little received her bachelor's degree in biochemistry and forensic science from Mercyhurst University in 2009 and her PhD in chemistry in 2017 from the University of Kentucky. So with that, I will pass it over to Liz.
Thanks, Megan. And I'm delighted that Cass was invited to be a part of this series. So I'll start by talking a little bit about Cass, and then I'll get into Tony's introduction as he is speaking first. So Cass is a relatively new center, started in 2016 through the Vice President for Research and Partnerships at the University of Oklahoma. And our mission is to help design, develop and use all types of autonomous systems in the air, in the water, and on the ground for environmental sampling and sensing. So while our group tends to have a strength in aerial vehicles for weather research because of OU's strengths in weather, we also have some experience doing autonomous boats and water sampling as well. Though that will not be highlighted in any of our talks, though you can go to our website at ou.edu/CAS to learn more about our Earth systems research, which is not represented in any of these talks. The next session will have something on the chemistry research that we do, though 3 of the talks will focus more on our weather systems. Our center has grown from just a group of 3 people, Dr. Philip Chilson, who is the director, and then 2 other people, to a vibrant team of meteorologists and scientists with 6 or 7 graduate students and a dozen undergraduate students, all working across a variety of disciplines to design custom systems to answer fundamental and applied research questions in the environmental sciences. So I'm delighted to introduce Tony Segales first, who is a PhD student in electrical and computer engineering, and his main research focus is regarding the development of the Copter Sonde, and he's going to be talking today a lot about the design process of an unmanned system to sense weather in a way that is focused on the science rather than driven by the hardware itself. It's more a science-driven concept. So with that, I'm going to turn it over to Tony, who they've given him his screen. So I'm going to ask Tony to take it away.
Sorry, now I found the unmute button. So thank you very much, Liz, for the introduction. Can you all see the screen?
Yep.
Yeah, okay. So thank you, Liz, for the introduction. So hello, everyone. First off, I want to give thanks to the organizers for letting us have the opportunity to share our work here. And I hope you all find this interesting. So as Liz said, I'm Tony Segales. I'm a PhD student at the University of Oklahoma, working for the Center for Autonomous Sensing and Sampling, CAS. And today I'm going to talk about the latest development, the Copter Sonde. So the Copter Sonde is an innovative drone which was designed and made in-house by us, the engineers at CAS, with the purpose of sampling thermodynamic and kinematic parameters from the atmosphere, in particular, the lower part of the atmosphere. So as an introduction, here's a brief history of the Copter Sonde. So the Center CAS was founded in 2016, same year as the very first weather drone was conceptualized, by just like throwing some weather sensors onto a commercialized drone, in this case, the Iris, as shown here in the upper left picture. So this drone was quite useful to start learning the pros and the cons. And based on these very first observations, we developed the Copter Sonde 1 here on the upper right picture in the year 2017. And so on in the next years, by learning from several field campaigns, several field experiments with different conditions, we came up with the Copter Sonde 2 and the Copter Sonde 2.5 in 2018. And it doesn't stop here. We're currently developing the next generation of Copter Sondes. So in this slide, I put everything more neatly. This is a timeline of the Copter Sonde with some remarkable developments done throughout the years, developments that radically changed the overall design of the Copter Sonde, and as well as seeing improvements in the data quality. So I'll walk you through each one of these developments that gave shape to the Copter Sonde. Starting with the weather sensor integration, the data streaming and distribution. So before going deep into the technical aspect, I want you to understand the design philosophy that we undertook. So everything starts by learning the end user's requirements, and in this case are the meteorologists. So they fundamentally want high resolution weather measurements in almost real time, coming from a very high endurance and cost effective drone. Also on top of this, to have the least errors possible. So for us, the engineers, we thought that the best way to start making a solution was to look into the software first, trying to see what the drone was already capable of doing, and then incorporate new features on top of that that could help shape the hardware of the drone. So at this point, it's a back and forth between the hardware and the software until you obtain the final design. So for the sensor integration, we opt to pipe all the weather data from the sensors through the autopilot. And we did this for the simple reason of eliminating unnecessary hardware. Like for example, extra data loggers. We found that the autopilot microcontroller is powerful enough to handle extra tasks and also extra data, meaning that the drone can endure longer in the air, consume less energy, be less prone to failure due to hardware malfunctions. And this is all because software is always going to be lighter than the hardware. So all the data collected by the drone is also streamed down to the ground station where it can be easily distributed to the end user through the internet. As shown here on the bottom, starting from the payload and moving through the autopilot, the telemetry, ground station, and the final user. Actually, we even developed a website where to store the data sets and that also any user can access it and also monitor the parameters in almost real time while the Copter Sonde is in the air. So the website is right here. It's open to the public, but also notice that it's currently under development. So now moving forward to the next feature in the timeline, the wind vane flight mode. So after integrating the weather sensors into the autopilot system, the next step was to find the best arrangement or the best layout of sensors on the drone. So we started with a symmetric layout, as shown here in the picture on the left. And each of these little cups around the body of the Copter Sonde contains one temperature sensor and one humidity sensor. And on the other hand, the Copter Sonde, this Copter Sonde here, the latest edition, the sensors are all put together in one spot at the very front part of the drone, right here. So this change was made to prevent taking samples from contaminated air, or I mean, disturbed air. So I'm going to elaborate on this a little bit now. So when the drones are subjected to wind, usually the wind carries the heat of the drone while it goes across its body. And therefore, in the symmetric layout version, the sensors behind the body of the drone are getting affected by this heat advection and thus giving wrong measurements. And and we've seen this happening in the field, actually, by watching the temperature plots in real time. We've seen this happening. So now in the new version, the new Copter Sonde design, shown here on the right, thanks to the localized placement of the sensors, we managed to significantly reduce the errors. And what actually enabled this to happen was the implementation of a wind vane algorithm, which keeps the Copter Sonde always facing into the wind, allowing for clean, undisturbed air to flow across the sensors while the body and the heat of the drone stays behind them. So in summary, the wind vane algorithm is our first implementation of an adaptive behavior in a weather drone that kind of mimics a rooster weather vane, just to put it in a different way. So the Copter Sonde does not have any dedicated sensor for wind sensing. It actually estimates the wind based on the tilt of the drone. And this is all for the sake of reducing weight as much as possible. And for doing so, we used some sophisticated digital filters in the process of the estimation. And once we got the wind vane algorithm working and all tuned up, then it was just a matter of optimizing the shell design for headwind airflow. So we have done several studies regarding this topic to try to provide with the best solution possible, and we're still having some breakthroughs. It's actually a never-ending project. So here are two of our papers related to sensor placement. You can check it out. I'm gonna drop the links after the talk in the chat so you can check it out. So now for our next remarkable development, the design streamlining and other improvements. So in my opinion, one of the most noticeable things on the Copter Sonde is the shell that covers the Copter Sonde, which is actually currently in the process of licensing. And it's 100% designed using CAD softwares and 3D printed in-house using strong PLA plastics. So as you can see here on the picture on the left, the 3D printer doing its work, 3D printing the shell. So the shell, besides protecting all the internal electronics from weather hazards or debris, the shell also has the functionality of housing the payload, as seen here in the 3D model on the right. So the weather sensors has their own compartment, which is integrated into the shell. And you can see here the intake where the air is sucked, the set of sensors right here, and the little fan on the bottom that aspirates air across the tube. So the shell is not only fully customizable, but it's also highly modular. So the payload compartment is completely independent from the main body of the Copter Sonde, as you can see here in the image, where the front of the shell is shown unmounted from the Copter Sonde, meaning that it can be switched with another payload at any given time. So this unique capability increases the range of types of sensor packages that you can mount on the Copter Sonde, and it all depends on what's being measured in the experiment. Oops, sorry. So here you can see another picture of the Copter Sonde with the payload compartment unmounted from a different angle. And also I'm going to show you a sequence of how it's mounted onto the drone, and it's quite easy, and it goes like 1, 2, and 3, just like that. It's quite easy and simple. So this shows the modularity of the drone to carry different sensor packages. So in these few remaining minutes, I want to show you very quickly the achievements we made with the Copter Sonde so far. Some personal records, such as flying up to 1,800 meters, that's over a mile high, in icy conditions, which actually happen in Finland. The flight endurance of 18.5 minutes in a very calm day. The Copter Sonde was also able to sustain itself in the air, actually in very thin air in Colorado. That was around 10,000 feet over sea level. It also withstood 22 meters per second wind speed when flying through a low level jet stream. And most importantly, the sensors, the electronics, the drone itself are still alive. They survive all those challenges. and they all remain healthy after 100+ flights. So every single of these achievements was actually very exciting moments for us. And given that the short time we've been working in this field. So I'm sure you also want to hear about the deliverables, the real after the fact results of using the Copter Sonde. And here they are, a Skew-T plot and a hodograph, and another plot of the evolution of the temperature over time. And I have to mention that all this was generated using programs made by our team of meteorologists, which are optimized for the Copter Sonde data. So for more in-depth analysis of the deliverables, I invite you to read our paper on the topic, which is listed here on the bottom of the slide, and which also I'm going to share it in the chat as a link. So as for my final slide, I want to give you a sneak peek of what is coming. So we've been working on the next generation of the Copter Sonde since last year. And this time we're dedicating our time to create a more user-friendly and robust drone that can ease the maintenance routines and also reduce human errors when operating it. So for example, the addition of a smart battery is quite convenient for the user because a smart battery requires less care, and it can also even auto-diagnose itself. So in few words, we are slowly getting to the point where the Copter Sonde will become fully autonomous. And if you want to learn more about the Copter Sonde and its developments and the case studies, here is you can check out this paper over here, which also I'm gonna share the link in the chat. So thank you very much for your attention. Here are our supporters. This is our website and also our Twitter account. And I'm happy to take any questions. Thank you.
Thank you, Tony. So anyone have questions for Tony that we can kind of dig into?
Yeah, Tony, I had a question for you in regard to measuring wind speed based on the tilt of the aircraft. I'm not really an engineer in that sense, so I'm not sure if I understood everything. Does the aircraft have to be hovering in order for that measurement to be accurate?
So yes, actually the current way we are taking sample is by doing a vertical profile. So basically the drone is steady horizontally, but it's only moving up and down. So it's a condition to be steady horizontally in order to be able to measure the wind direction by its tilt. Yeah, you're right.
One other question in that regard, if you were to change the internal components, you would change the weight distribution. Would that require a recomputing the tilt in order for it to be accurate?
So basically what we do with the Copter Sondes is that we actually calibrate them before delivering the results. So we calibrate before taking them out to the field. So whatever package or whatever payload it's carrying, we're gonna previously calibrate the Copter Sonde to try to get the best results out of it and then send it to the field.
Okay, thank you.
Tony, I have a question. If you have time.
Sure.
Have you any thoughts on doing multiple measurements, for different variables at the same time, so you will add more capability to?
Like what, for example?
Well, it can be anything related to weather,
So currently the Copter Sonde is measuring temperature, humidity, pressure, and wind direction and speed. but we are thinking of designing different scoops, different front shells to carry different other packages. Like for example, could be aerosols, it could be measuring CO2 or ozone. So that's the beauty of this. You can swap these front shells in at the field, and you can measure different things with that one single system. But currently, we're measuring more like thermodynamics, like temperature, humidity, and the kinematics, which are the wind speed and direction.
Great, thank you.
We still have a few minutes left for questions. If anyone has any other questions they'd like to ask of Tony.
I have one more, if I may.
Absolutely.
From the regulatory standpoint, anything you have had to do regarding that?
So we are working very closely with the FAA. It is true that we are limited in the legal aspect, because the FAA limits us to fly up to 400 feet. But with some special permissions with them, we can actually go up to close to 5,000 feet. But it's only in very specific areas in the state. But we're trying to work with them so in the future we can show them that our system is safe enough to operate in the airspace.
Thank you.
I have a question for y'all. My name is Mark. I'm at the Academy in Oklahoma City. So do these drones have the remote ID that the FAA is requiring or starting to require for the RC remote control airplanes and various kinds of drones, so that they can be tracked on some sort of a radar type tracking system?
So I've heard about the remote ID. I'm actually a hobbyist. I know all about what is going on in the world of the hobby and the remote ID. So we're trying to learn as much as we can now, so that we are prepared at the moment they are going to release these rules. So currently the FAA knows that we are flying without a remote ID, but we're still having the permissions from them to be able to fly out in the field. But eventually we're gonna get ready for this remote ID. Right now the drone is able to stream all the data down to the ground station, so we can upload those to any database from the FAA, so that it can see that we are, so that they can see that we are flying, so that they control.
Okay, so how high did you say these things go?
So say again.
So how high do you fly these for the soundings?
So our record with this drone was 1,800 meters. That's a little bit over a mile. But right now with the FAA limitations, we are the highest we can go is 5,000 feet. That's around 1,500 meters, if I'm not wrong. Yeah.
So is your plan to go any higher? I mean, because there's various layers of airspace that you'd be trying to violate. Are there any plans to be able to get a clearance to climb up into even the flight levels?
I mean, yes. I'm pretty sure that meteorologists wants to go higher, but right now what it's limiting us is the battery technology. Okay. So eventually, when once we get this new technology, battery technology, we could probably go higher. So my calculations are that this Copter Sonde currently can just go up to 2 kilometers up.
Okay, thank you very much.
Yep.
All right, any further questions for Tony? If not, Liz, if you want to go ahead and introduce Tyler, we can move on to his presentation.
Also, people check out the chat. I'm gonna send the links there.
Yes.
So thank you very much.
Thank you, Tony.
So while we're changing slides, I I will also touch on the airspace thing. We use certificates of authorization to go high, and it's all targeted on where the airspace is allowed. And we usually use class E and G spaces to avoid areas where we cannot go higher into the airspace, so that we can avoid those problems. There's no way we can go class C, for example, at that airspace height. We work very closely with someone who is well-versed in airspace to help us select appropriate areas. But of course, as things get more autonomous and things like that, we'll work to sort of enter the airspace more appropriately. So that is always a concern that we're working on, but yes.
So you work under TFRs right now? TFRs?
Say that one more time for me.
TFRs, temporary flight restrictions, where they give you a TFR's airspace and you can use that.
We have a 2-year certificate of authorization we apply for. It's a 107 COA that we use. It's similar to what you would do with a 107 waiver, but it's a little stronger for a specific area. Like where we do have a big one now is out at our flight field at Purcell. And we have a 1 nautical mile cylinder that we can go surface to 500 or 5,000 feet during the day. And
is that active all the time? Oh, during the day, daylight hours?
Daylight hours with a NOTAM. So we'll put the NOTAM up, it'll be active at a certain time, and then it'll come down. But we use NOTAMs and COAs for our stuff.
So I'm looking at it as an air traffic control perspective, because as a controller, they're going to have to make sure no other aircraft are violating.
Oh, absolutely. No, we work, and we've been discussing some stuff with the control tower at Westheimer here in Norman too, to learn things. But yes, we are very cognizant of using NOTAMs at all times so that people know where we are.
Very good. Thank you.
Of course. But this is always a hot topic. We are aware of remote ID, and we will be putting stuff on our vehicles when it comes time. I assure you that. So we'll transition to Tyler's talk, which is kind of growing out of what Tony was doing. So Tyler is a PhD student in meteorology at OU and also works as a research associate at the Cooperative Institute for Mesoscale Meteorological Studies, or SIMS, at the University of Oklahoma as well. And he is studying combining unmanned systems with traditional meteorological techniques to find how we can create a new way of measuring the atmosphere where we combine all of these technologies to get a more cohesive picture. And so he is particularly going to be talking about using the wind vane mode that Tony was talking about during his talk and comparing it to more conventional techniques and how that has come out. So with that, I encourage Tyler to take it away.
Thanks, Liz. Can everyone see my screen okay? Yep. Awesome. Thank you. So like she said, I'll be talking about a little bit about some of the work Tony and I have been doing, trying to improve the wind speed estimations from the Copter Sonde. So I'm one of the end users because I'm a meteorologist, so I'll also give you a little bit different perspective than Tony did. So, come on, switch. There we go. So it's pretty widely accepted within the meteorological community that we really need more observations of the atmospheric boundary layer. The atmospheric boundary layer is typically lowest 1 to 2 kilometers of the atmosphere, and it's also the part we live in, so it's pretty important. And lastly, it's also one of the most dynamic parts of the atmosphere. So the easiest way I've come up to display this, what we call the data gap, is with this figure in the lower left. So what you're seeing is a time-height plot, so time on the x-axis, height on the y-axis, and then the color fill is temperature data. So most people are probably familiar with observations that are taken at the surface with something like a meteorological tower. Generally, it's 10 meters, and you can get pressure, temperature, humidity, wind speed, wind direction. So you can see a 24-hour time series of temperature data here at the bottom. And then the National Weather Service all around the country launches 2 radiosondes or weather balloons a day. And so you can see those here. However, there's a lot of white space still. So this is what we reference, or what I'm referencing when I talk about the atmospheric data gap. If we look to the right, this is what that same day looks like with weather UAS observations from the Copter Sonde. And this is doing a profile every 30 minutes to the highest altitude we can safely at the time. You see, this is a much higher fidelity look at the atmospheric boundary layer as a function of time. And you can see just how much it changes throughout the day, and that isn't captured at all in our typical observations. So here I'm showing temperature, but like I said, temperature, pressure, humidity, wind speed, wind direction, those are all important variables and kind of the base state variables for a meteorologist. So as Tony alluded to, we measure wind speed not using something like a temperature or a anemometer or something mounted on the drone, but we use the tilt of the drone itself. And we try to stay at the same lat long, and in order to do that, we have to counteract the wind, and we get some sort of tilt from this, right? So if you start to do the math, you can use your force balance equation, balancing force of gravity, the drag force from the wind, and then the thrust vector. And if you assume you're not accelerating, set all that equal to 0, you can do some fancy math and bring in the Rayleigh drag equation. But ultimately what you get is this relation down here. You can relate the velocity of the wind to the square root of 2 times the force of gravity times the mass of the craft divided by the density of the air, the cross-sectional area of the aircraft that is perpendicular to the wind vector, and then the drag coefficient. And you multiply that by the tangent of this tilt angle here. So one of the great features of the Copter Sonde that Tony's already kind of talked about is it's always facing into the wind. So really this tilt angle is only the pitch angle. So you immediately take out a lot of degrees of freedom from the equation and can make it simpler. However, we still have these pesky terms right here. This cross-sectional area as a function of the wind vector, and then the drag coefficient. And unless you're a really good computational fluid dynamicist and have a really high fidelity model of the Copter Sonde, these are actually really difficult to calculate. So what we like to do is just lump all of this harder stuff into a coefficient that we bring out to the front. And so this provides a very, very nice and simple equation to relate the tilt of the craft to the wind speed. It's just a perfect linear relation. So what we typically go and do, as again Tony alluded to, is we go and take the Copter Sonde out to a meteorological tower and just hover next to it. And then we grab the data from that tower, we grab the tilt angles from the copter, and we can empirically derive this coefficient here. And then after we figure out what this coefficient should be, anytime we have a tilt of a copter, we can multiply by that and get the velocity of the wind. So super simple, and this is a pretty widely used technique within the weather UAS niche field. But how do we actually know that it's working? Because like I said, we have an atmospheric data gap, so we don't really have very many observations above the surface where we like to fly. So what I've done is combined a different type of sensing technique, which is remote sensing. And so being at OU, I'm also fortunate to have access to the Collaborative Lower Atmospheric Mobile Profiling System. And so this is a suite of instruments that are also meant to try to fill this atmospheric data gap. But instead of using in situ measurements like the Copter Sonde, we're using remote measurements that are taken from the ground and representative of a profile. And this system has taken part in a lot of different field campaigns, 2 of which I'm going to talk about here in a second, are lapse rate, which was in the summer of 2018, and flux capacitor, which was in October 2018. So how do we actually get the wind with clamps? It's got 3 instruments, one of which is for kinematic profiling. This is the halophotonic streamline scanning Doppler Lidar, and it is this instrument that's sticking out the top right here. So you can think of a LiDAR kind of like a radar, weather radar, except it uses light instead of radio waves. And it also is much higher resolution, specifically in the wind field. There's 2 other instruments, part of clamps, that I'm not going to talk about in depth here. And they are both radiometers that measure downwelling radiation from the atmosphere in both the microwave and infrared spectrum. And from that, you can put it through a retrieval to derive the temperature and moisture profiles. Okay, So like I said, we were in 2 different field campaigns in 2018. The lapse rate, this stands for Lower Atmospheric Process Studies at Elevation, a remotely piloted aircraft team experiment. If you didn't know, meteorologists love acronyms. I'm just gonna put that out there. And then the second one is flux capacitor campaign. And so both of these campaigns, we had clamps and the Copter Sonde and radio sondes all co-located with each other. And so this allows us to do very in-depth intercomparisons between the various systems that are meant to take the same type of measurements. So lapse rate took place over here in the San Luis Valley in Colorado, and then flux capacitor took place at our flight area, which is south of campus, the Kessler Atmospheric and Ecological Field Station. This is where we have permissions to go to 5,000 feet during the day. And you can see it's quite different types of terrain. So we get quite a range of different conditions here. So one of the papers that Tony posted, the one I wrote, has these results in it. And like I said, I'm only going to concentrate on the kinematic results. If you want to know more about the thermodynamics, you can read my paper. And that should be 2020, not 2010. So if you look here on the upper left, this is me comparing the Copter Sonde wind speed on the x-axis, what was measured. And then on the y-axis, we have the Doppler Lidar measured wind speed. And then here on the upper right, you can see a histogram of the differences. And ideally, the differences would be 0, but you can see that's not exactly the case. Copter Sonde is actually underestimating the wind speed by anywhere from 0.5 to 0.7, 0.8 meters per second, which is outside of the accuracy we're trying to achieve with the Copter Sonde. So that's not ideal. You can also see it over here on the upper left that at higher wind speeds especially, we're underestimating the winds. And this goes all the way up to 22 meters per second approximately, which was the record that Tony mentioned. So me being the meteorologist and wanting better data, I was like, well, what the heck can we do better? And I thought of 3 different causes. The first of which is that maybe the tilt of the craft is different while it's ascending as opposed to while it's hovering. So like Tony and I both described, the way we would calibrate this coefficient is we would hover next to a meteorological tower and relate the wind speed to the tilt of the craft. But when we're actually in operation, we're not hovering, we're actually ascending at a constant speed. So maybe while this is ascending, the thrust vector is pointed more down because the tilt of the craft is less. And so the calibrations that we do hovering aren't necessarily valid while we're ascending. Additionally, in Colorado, we're at pretty high altitude, up to 10,000 feet above sea level. And that's a lot different than Norman, Oklahoma, where our density of the air is much higher. And we did all of our calibrations in Oklahoma. So maybe the density correction needs to be done. Goodness. So fortunately, because we do have a thermodynamic sensing package on the craft, we can directly calculate density. So we might as well pull this density value into the independent variable slot and derive a new coefficient from that. Maybe that would help. And then lastly, the last thing I thought about was, well, maybe a linear fit isn't the most appropriate fit to apply to the data. So on the right, you can see a plot of us comparing the wind speed from a mesonet tower, 10-meter tower, to the tangent of the tilt angle. And if you fit a line to all these data points, you get this equation. Well, you can see our y-intercept is negative 6.37 meters per second. So this would imply that at 0 tilt, we're measuring a negative wind speed, which doesn't make physical sense. So obviously something needs to be changed there. Additionally, maybe the projected cross-sectional area that I talked about isn't necessarily a linear function. So that could also mean that it's more of a quadratic or some other type of function. So the easiest way to test this was to use data from these 2 campaigns. I picked out a single Copter Sonde tail number and randomly chose 15 of the 80 profiles I had of all this co-located data. And then using these 15 profiles, I would train the algorithm and then test it on the rest of the data and see how it improves. So on the right, you can see how we're relating the VAD or the LiDAR wind speed to the tangent of psi. And you can see we're still at kind of a negative y-intercept, which isn't what we want. So the LiDAR uses a technique called the velocity azimuth display. Essentially, it's a way to take line of sight measurements and turn them into UV and W measurements. And then I also had pretty strict requirements for the comparison to be valid. And I can talk more about that later if anyone's really interested in it. So just to remind everyone, this is my control case. So this is the single Copter Sonde. And you can see it's still underestimating this wind speed by, up to 1 meter per second if you look at the median. So what happens if we calibrate while ascending instead of hovering? You can already see a pretty big difference here. So our median difference goes from almost 1 meter per second bias to less than 1/10 of a meter per second. And then our mean is also very low. So immediately, just taking into account the different tilts, we can drastically improve our results just by calibrating while ascending instead of while hovering. And so next question was, well, what happens when you add in the density? And really, surprisingly, not much. I'll flip back and forth here to the before, after, before, and after. You don't see a whole lot of difference. So the density really didn't have much of an effect on the overall wind speed measurements, which was kind of surprising to me because I figured the thinner air would have a higher impact. But so even with this density correction, you can see that we're still slightly underestimating things at high wind speeds, especially. So what happens if we move away from this linear fit and move towards a quadratic fit instead? Well, we start to do better at higher wind speeds, even overestimating a little bit, the very highest wind speeds. But overall, this is a much better improvement than what we started with. And just to give you an idea of what this quadratic fit looks like, you can see it here. And I've forced it to be physical by making it go through 0 and have a y-intercept of 0. So that means if we're just hovering flat because there's no wind, it'll say there's no wind instead of there being negative wind. And you can see it fits pretty well. It fits this higher wind speed data even better. So combining all these effects, we get much better estimations of the wind speed, and we're within the bounds of the accuracy we're trying to achieve with this system now. So that was a lot of information really fast, but just to conclude, the first thing I conclude is that comparing this weather UAS system, the Copter Sonde, and a Doppler LiDAR is actually useful. That's not something that's really been done before because they're two totally different trains of thought in the meteorology world of filling this gap. Second, using the Doppler LiDAR to calibrate this Copter Sonde while ascending and using a quadratic function has the most overall effect. However, in the future, we're also going to go ahead and include that density correction just because we can do that calculation anyway, and it's probably the most valid thing to do. Of course, meteorologists always love more data, so I'd love to get more data sets to do more comparisons with. And using this random selection of profiles, we should be able to bootstrap it and start to get some uncertainty within our wind speed estimations. So uncertainty is incredibly important when you're doing data assimilation for models, because you need to assign some sort of possible error to your observations so you don't overfit your data. And then lastly, Tony and I are starting to explore some more complex methods of wind speed estimation that has to do with some digital signal processing, which Tony's much better at than I am. So with that, I'll take any questions that anyone might have.
So Tyler, my question is, wind speed varies from moment to moment, doesn't it? It's always changing. So I'm wondering whether some of the error that you're getting is simply because you don't get the same wind speed from one fraction of a second to the next.
Yeah, certainly. That's that's why we needed such an expansive data set to do this, is because of how much variability there is in wind speed. You can have a gust that's completely different from the mean wind speed. And you could just measure that gust with the Copter Sonde instead of anything truly background related. So the way we tried to get around that is just by having a lot of data so we can get really good statistics and try to get the statistics converge.
Any other questions for Tyler?
I just have a comment. It's very impressive, the work that you're doing and sitting with Alex. So thank you for sharing this.
Yeah, it's fun work, and it's amazing how detailed you can get into the analysis.
I also want to add a comment. First, strong shout outs and kudos to the whole team that's been working on developing the Copter Sonde, and on the point that someone raised about the non-homogeneity of the wind field, and that's definitely a valid point. In reviewing, getting this paper reviewed into the literature, one of the reviewers pointed out that same effect, and Tyler actually compared radiosonde data with the Copter Sonde and seeing some really cool variability in how clouds are formed, which he didn't show, but it's just pretty exciting. And I would say that in the meteorological community, people tend to take radiosondes as being the gold standard, but I think what people who are on this call are witnessing is the beginning of a new era where I think these types of measurements are going to become the new gold standard when you start making temperature, pressure, humidity, and wind measurements aloft. So this is really exciting.
I just want to make a correction. I thank Alex, but I meant Tony. So sorry about that, Tony.
All right, any other questions? All right. Liz, any closing comments before we all part ways?
We're doing this again in 2 weeks. I do believe it is exactly 2 weeks, if I am not mistaken.
So it'll be June 25th, yeah.
June 25th. It will be 2 of our other students will be presenting on their work. We'll have 1 meteorologist and 1 engineer speaking. So one will be about a sensor development or a sensor payload that's being developed for monitoring carbon dioxide. So that's more my research area. So that's atmospheric chemistry. And then our meteorologist will be speaking on, I believe, atmospheric turbulence. I see nodding, so I'm right. That's great. And of course, as always, if you want to know more about what our team is doing to advance environmental sampling and unmanned systems, you can always check us out at our website or on Twitter at OU_CAS. We are pretty active on there. We do not have a Facebook, so you won't find us on there or anything like that, but you will find us very active on Twitter. Our stuff seems to share well on Twitter because it's mainly photos. We like to take pictures of our drones and things in the field. So, and you can always reach out to us too on the website. There's some emails and ways to get a hold of us if you want to know more about a particular topic, as well as all of the links to all of our publications about what we do. So if you want to learn more, there's lots of ways to learn more about what we're doing. And we would love to answer your questions if you got more about that.
Thank you, Liz. I want to say on behalf of the Oklahoma City Innovation District, we are so excited to bring this and coordinate this together today. Huge thank you to Dr. Chilson and Dr. Pillar Little for helping us organize this. Again, we're so grateful for this partnership and look forward to doing a lot more of this in the future. Again, if you're interested in knowing more about the Innovation District, check out our website, okcinnovation.com. All of the links to our social media accounts are there. And again, we'll be sending out more email blasts about the upcoming event on 2 weeks from today, on June 25th. So we really look forward and hope to see everyone there again in 2 weeks. So thank you all for participating, and I hope you have a great rest of your week.
Thank you, you as well.
All right, thank you. Bye-bye.
Thank you very much, everyone.